We can start. Good morning, everyone. Welcome back to this new webinar on our energy data and modeling program here at the IEA. Today's webinar number 11. As you know, the topic is the SDG7.1 and will be focused on solid biofuels, clean cooking, and electricity access. So I will go back to our agenda. As you can see, we are almost at the end of our program. The next two lectures and webinars we will have, one will be this Thursday, so the day after tomorrow, and another one, so the last one will be April 26th on next Tuesday, so in a week. So today, as I said, the topic is SDG 7.1. Thursday, we will be focusing on solid biofuels estimation models, and then we will wrap up the overall program, having some quiz and closing. So we will be also closing this program, at least the first part. So here we have the educational objectives of today's webinar. So we will discuss into more details the following two topics, as I said. So solid biofuels, which, as we know, are very important in sub-Saharan Africa, but there are many barriers and difficulties when it comes to collecting data and treating statistics that refers to solid biofuel. But still, there are available right now today interesting analysis on those practices and also on clean cooking numbers. So we will end this part on the solid biofuels and cooking by looking ahead of potential outlooks, modeling principles, so to try to assess what the future could look like when it comes to the consumption of solid biofuels. And in particular, when it comes to the number of people having access to clean cooking fuels. So we'll break between these two modules. We will have a quick exercise focused on access to clean cooking. And then in the second half of this session, we'll discuss access to electricity and focus specifically on off-grid electricity, off-grid electrification. We'll also go through an overview of this topic. Then we will discuss data and statistics and conclude by having a look at the modeling implication of this specific topic. So, for example, how we can do long-term projections on electricity access, on access to electricity. What, for example, could the future look like in terms of required investment for example, providing access to electricity to millions and millions of people? And for example, what are the CO2 emissions related to this, let's say, increasing number of people having access to electricity, depending on the technology we are providing them electricity with. And yeah, so more or less, this is the overview for today. In particular, off-grid electricity and access to electricity is the topic I'm working on in my daily life, let's say. So if you have questions with respect to that specific topic, which I think is really relevant and important, especially when we talk about sub-Saharan Africa, as usual, feel free, but not necessarily just for that, also for the solid biofuels and access to clean cooking session. Feel free to put your questions in the Q&A box. Otherwise, I invite you, and it's even better, to raise your hand through the Zoom functionality, and I will give you the floor so that you can unmute yourselves, turn on your camera, and directly ask the question you doubt, or also just giving a feedback from your perspective on these two very important topics. So before starting the actual presentation, I would like to do a quick polling, as we are used to do. So the website is always the same, www.com, .menti.com. I will put in the chat in a few seconds the link and also the code that you may use to access today's questions, today's polling. So this I'm copying here is the link, and this is the code. So I remind you, www.menti.com, and then the code is 51881803. So the first question is, how many kilograms of food, of wood do you need to produce 1 kilogram of charcoal in a traditional earth kiln? So you have three options. We have approximately 2 kilograms, we have approximately 5 kilograms, and we have approximately 10 kilograms. So again, how many kilograms of wood do you need to produce 1 kilogram of charcoal in a traditional earth kiln? Okay, so we have already 2 people which answered, and 3, so all people are answering approximately 5 kilograms. We have 3 questions, so I give you a few seconds more for the other people which maybe weren't so fast in connecting to menti.com. Okay, I see new additional answer. Okay, I don't see any other answer. So here the correct answer was, let's say, okay, so another one, additional, okay. So the correct one in this case was, let's say, our estimations in terms of production of charcoal around the world are between 5 kilograms and 10 kilograms. So it really depends on the efficiency of the art kiln you're using. But let's say that the most traditional models, for example, have values which are very close to 10 kilograms. So all of you were right, actually. But it really depends on the context and the efficiency of the specific art kiln you're used. So next question is, rank the best solutions for achieving universal access to clean cooking. So you have 5 technologies, 5 solutions. You have LPG, you have electric cooking, you have biomass improved cookstoves, you have biodigesters, so which use biogas, and a combination of all these options. So the question is, rank all of them with respect to what is, let's say, your thought on which of them is the best solution for achieving universal access to clean cooking. I see one person answered a combination of all of these options. 2 people. Then we have LPG cooking, okay. Okay. Okay, so 4 people, I give you a few seconds more, but right now we have, let's say, a picture in which we have a combination of all these options. Then we have LPG, we have electric cooking, and then we have biodigester and biomass improved cookstoves, which are the 4th and 5th place, but are very close one to the other. So I won't give you, let's say, an answer here. As you may anticipate, a combination of all these options is probably the best option, because we don't have, let's say, one technology which is suitable for everything. It's a bit unrealistic, but in the next lectures, in the next slides, you will see what is the result of our modeling with respect to this question. So next question is just a quick poll. It's not there is no right and wrong answer. We just want to ask you, in your household, what fuels, so there may be more than one, do you use for cooking? So do you use food? Do you use charcoal? Do you use LPG? Do you use electricity? Do you use kerosene or others? So I see that, okay, we have LPG, electricity, and charcoal, which are, okay, so very diversified. And it's interesting that we have many more answers with respect to the number of people which answered to this question. And this is nice because it really means that many of you are using multiple fuels for cooking. So that's a very interesting point, and which will also be raised by the slides you will see today. Okay, perfect. So I will go back. Oh, sorry, there is a question, I think, in the chat. Okay, thank you very much, Dr. Francis. I don't know if all of you read the comment, but our colleague is saying that ethanol is also starting to become an interesting option for cooking. Yeah, thank you very much for this feedback. Okay, so I will go with the presentation. Let me know in the chat if there is any problem with sound, etc.
Let's get started with solid biofuels and access to clean cooking. We will look at the importance of solid biofuels in sub-Saharan Africa. African countries and is used primarily for cooking purposes and then for producing electricity. First, there is the cultural preference of some people who prefer to cook using firewood traditionally, but there is often an accessibility issue in rural areas for other sources of energy such as LPG, and so firewood is usually the most accessible fuel for cooking. In urban areas, even if modern fuels can be accessible, we might have the issue of affordability as these modern fuels are more expensive than wood. So even if alternatives exist, people still continue cooking using biofuels. Now let's see what are the impacts of using solid biofuels. The use of solid biofuels is not without consequence for the health of the population. Studies have shown that more than 500,000 people die every year from pollution from biomass cooking. This is more death compared to diseases such as HIV, malaria, and tuberculosis. Other drawbacks of using biomass is that women also suffer from wood collection and spend several hours daily picking biomass. There are also safety consequences as they usually go alone in the forest. If the use of biofuels and wood is not done in a sustainable way, then there are negative impacts on the environment. If there is no balance, then the forest is reduced. It is also important to collect good biofuels data for policy making in order to guarantee that we ensure clean cooking access, proper regulations for charcoal production, etc. Therefore, tracking biofuels production and consumption is key for countries in sub-Saharan Africa. Now let's put things quickly into perspectives and see how energy demand has evolved over the years. In 1919, wood accounted for around 1/3 of total energy demand. Over the years, we see how energy demand transitioned to oil, natural gas, etc. The share of wood decreased a lot at global level, decreasing from 30% in 1919 to only 4% in 2017. But in absolute value, biofuels rose by 2/3 from 400 mtoe in 1919 to 650 mtoe in 2000. Since 2000, as developing countries move away from the traditional use of biomass, the absolute consumption drops from 650 mtoe in 2000 to 620 in 2018 and 550 in 2040 based on the stated policy scenario. Now, if we look at final consumption, we see that in OECD countries, biofuels and waste is not significant, and in non-OECD region as well, it accounts for only 15% of consumption. However, if we look at Africa, the share increases to over 50%. And in sub-Saharan Africa, it is even larger, accounting for 3/4 of total final consumption. We have seen that biofuels are the highest consumed fuels in sub-Saharan Africa. In sub-Saharan Africa, the biofuels consist mostly of primary solid biofuel such as wood and then charcoal. Now let us see more in details what we include under biofuels and waste. First, it includes primary solid biofuels such as wood, but also biogases, charcoals, bioliquids, as well as industrial and municipal waste. In OECD countries, we use mostly modern biofuels and also bioliquids such as biogasoline, biodiesel, and bioethanol. These are mostly used in transport, whereas for waste, they are usually used for electricity generation. Now, if we look at Africa, we see that it consists mostly of primary solid biofuels and charcoal that is considered as traditional use of biomass. And in sub-Saharan Africa, it is even more primary solid biofuels. Now, let us see more closely at what are solid biofuels. Solid biofuels covers organic, non-fossil material of biological origin. We can make a distinction between primary and secondary biofuels. Primary production is the capture or extraction of fuels or energy from natural energy flows, the biosphere and natural reserves of fossil fuels within the national territory in a form suitable for use. Inert matter removed from the extracted fuels and quantities reinjected, flared, or vented are not included. The resulting products are referred to as primary product. Secondary production, on the other hand, is the manufacture of energy products through the process of transformation of other fuels and energy, whether primary or secondary, such as charcoal. Only the amount specifically used for energy purposes, that is a small part of the total, are included in the energy statistics. Let's see how solid biofuels consumption is evolving in different regions. First, we see that in 2018, sub-Saharan Africa accounts for 1/3 of total solid biofuels demand, and if we look from 1990, we see a constant increase in demand that nearly doubled in the last 30 years. In the rest of the world, demand has remained quite stable. This shows that we are still increasing the use of biofuels and access to clean energy sources are slower than population growth that is increasing very fast by 3% annually. But where are solid biofuels consumed? In which sectors? In OECD countries, less than half is used in residential sector, mostly for heating purposes, and a big part is also used in industry for raising heat in industrial processes. However, in non-OECD, a big chunk is used in the residential sector. If we go to Africa, most of the solid biofuels is used in the residential sector and for cooking purposes. However, these numbers could be lower or higher because of data uncertainty. This graph shows household consumption for cooking purposes in rural and urban areas. And we can see clearly that there are some differences between rural and urban consumption patterns for fuels. In urban areas, we have a bit more fuel mix for cooking, where we have some use of LPG, kerosene, and electricity. However, in rural areas, it is still primarily fuel wood and charcoal. We often know how much kilo of wood that we collect, but how much energy does that wood contain? This is one of the barriers of biofuels data collection. The net calorific value, it's the useful energy, and the moisture content is also very important. Depending on how moist the wood is, the calorific value varies. Normally, when you cut or collect wood, it has a moisture content of around 55%. But if you dry the wood and reduce the moisture content to only 20%, then you see that the calorific content is more than twice than the wood with a moisture content of 55%. The efficiency of the combustion will be more, and it will be also more healthy. Now, if you transform the wood into pellets, then the calorific value is even higher. It is often the case in Africa that the wood is used fresh because of lack of space for storing and also the danger of being stolen. So in Africa, the average net calorific value of wood is around 7 megajoule per kilogram. And note that for comparison, that for LPG, it has a net calorific value of 50 megajoule per kilogram. So there's a big difference between the two. The production of charcoal is an output of a transformation process where wood is considered as the input. Note that the calorific value of charcoal is much higher than firewood. Note also here some important facts about charcoal production. The efficiency of the charcoal kiln varies quite a lot from 10 to 40% depending on the technology used, and in sub-Saharan Africa, this is often very low. To produce 1 kilo of charcoal, you need a lot of wood, and in energy units, the efficiency can be as low as 20%. But if you have good wood, why do you need to transform it into charcoal? Charcoal is a better energy product. To have the same energy as 1 kilo of charcoal, you need to burn 2 kilo of dry wood. However, if you use moist wood, then you will need even more. Often in Africa, firewood is consumed without drying, because storing it might mean it will be stolen, and there's also not space. So its quality when burned is lower. Firewood net calorific values are very variable depending on the type of wood and the moisture content when it is burned. In average, we can assume that it is 14 megajoule per kilogram. Charcoal, on the other hand, is a higher quality energy product with a calorific value of around 30 megajoule per kilogram. So it is more practical to store and transport charcoal because with the same energy, you need less volume and weight. However, the transformation of wood into charcoal has a lot of impact. To produce 1 kilogram of charcoal with traditional earth kiln, you need up to 10 kilo of wood. So you need a lot of wood and so a lot of trees. Therefore, it can lead to deforestation if it is not done in a sustainable way and will affect the environment and lead to deforestation. However, with an improved kiln, it can be better and the yield efficiency is around 30% and you can produce more charcoal. So it is very important to track how charcoal is produced in the country as it has an impact on the environment. Let us look even more at the end-use energy service, that is cooking. Here we will see the different type of fuel, so wood and charcoal, and the means for cooking, that is traditional stove and improved cook stoves. With a traditional stove, you need around 5 kilo of wood to cook a meal. But if you use charcoal, you need only around 1.65 kilogram of charcoal. Then to produce this charcoal, you will actually be consuming 16 kilogram of wood if using an earth kiln. So in the end, when you do a complete analysis, you are actually consuming more wood. The life cycle analysis shows an efficiency of 5% only. If you use an improved kiln to produce the charcoal, you are actually using around 6.7 kilogram of wood to produce the charcoal, and the life cycle analysis shows an efficiency of 14%. In an improved cook stove, you need just 3 kilograms of wood to cook a meal, which is better. And if you use charcoal in an improved cook stove, you need even less, that is only 1.15 kilogram of charcoal. If that charcoal is produced in an earth kiln, you will need 11.5 kilogram of wood to produce the charcoal, and the life cycle analysis gives a real efficiency of 7%. In an improved kiln, you need only 4.6 kilogram of wood, and the life cycle analysis or value chain impact is better and gives you 19% efficiency. Therefore, even if charcoal cooking is more efficient than wood cooking, at the end-use stage, the impact on wood resources and deforestation can be much higher. With the increasing urbanization, the demand of charcoal could drastically increase if sound policies are not in place. Why do we have this impact on climate? If you have a forest, this forest is absorbing CO2 emissions and storing the carbon in the wood. Now, if you cut the wood and burn it, we release again CO2 emissions. And if we do this in a sustainable way, we have net zero emissions. And if there is an equilibrium, there is no net emissions. However, if the amount of wood is not cut in a sustainable way, that is, we cut too many trees, then the amount of CO2 release from burning the wood will increase drastically. And at the same time, the forest too will diminish, leading to a disequilibrium, and we will end up with positive net emissions as the absorption of the forest is much less. So if there is no net equilibrium, we have net emissions, which is positive. Now, let us move to the second point on the barriers and best practices for collecting solid biofuels. For biofuels, if we focus on primary solid biofuels, we see that all the products are combustible energy commodities which can be traded and stocked. The consumption of these products will be either as a transform to secondary product or as blended to the other sources or usually in an end-use application. But how do we get these data? We get them from sales data, for example, from wood and charcoal sold in markets and consumption data. But here we also lose a big chunk of data as we miss the black market sales and also some people pick wood directly in the forest and so do not buy it. What are the common barriers? As you have seen, we have this issue of commercial and non-commercial fuels. But we also have a need to have a correct sample, and it is important to work with the statistical office of your country to have a representative sample for both urban and rural areas and also by regions. We need to collect data by type of solid biofuel used, as regional wood resources are different with different calorific values and moisture content. There is also the cultural difference to take into account because different people cook in different ways, etc. There's also different types of appliances, different cooking stoves. We need to cover both commercial and non-commercial biofuels and include charcoal as well. For non-commercial, we need to track how much wood is picked, the reselling, also the unregulated charcoal production. There is also a need to understand how charcoal has been produced in order to estimate the fuel wood input. So what type of kiln has been used? So is it traditional kiln or improved ones? Now let us see what tools we have at our disposal to establish a methodology or an action plan to track residential consumption and biofuels demand. For the observed data inputs, we can find information from administrative data, surveys, and measurement. Using those input with some assumptions of calorific values, consumption of stoves, and energy by device, we can derive some estimations using modeling in order to have complete data output for energy by source, by end use, and also calculate indicators. Let's see a bit more the tools and data needs. This is not perfect, but we try to give relevance to each one. For example, if we leave it blank, then it means that it is not the best practice. But if it is green, it means that for this data need, this is the preferred data source. Estimation and modeling. Here we have to be careful as consumption patterns change, and we can't just assume that people consume in the same manner as 20 years ago. So there is also access to clean cooking to take into account. Note that it is important to continue collecting resources data, that is forest data, as well as charcoal production by type of plants. It is essential to track how sustainable biofuels consumption is. Now let us go even deeper into an action plan for solid biofuels data. How will we start? In 2010, let us assume we have a survey for household consumption by type of fuel. And we also know that the number of households. And with this information, we can calculate the total of charcoal, fuel wood, and LPG. Then for the next 5 years, we don't run any surveys and we just use qualitative data from census. Then we can estimate the missing years, but beware that we cannot use the estimate for many years as they lose their value over time. So if we use the qualitative data and add it with the number of household by type times the intensity, we can calculate for 2011 up to 2015. In 2016, there is another survey that is done. And here we will get observed data, and this will also permit us to revise previous data, estimated and old surveys data if we collect even more detailed data. Survey results help us calibrate qualitative data for estimations. It is true that surveys are costly, but it is even more costly not knowing what is happening. Now, we are going to deal with the last part of solid biofuels, and we will look at clean cooking status and modeling. Solid biofuels in developing countries are mainly used for cooking, a topic covered under the Sustainable Development Goal 7. There is the first target, which is 7.1, that ensure universal access to affordable, reliable, and modern energy services. And we have the indicator 7.1.2, which is the proportion of population with primary reliance on clean fuels and technology. How do we define clean cooking facilities? We have several technologies for cooking, and we define as not clean cooking technologies when we use biomass, coal, and kerosene. Note that for biomass, only the traditional use of biomass is not clean, and if you use an improved stove, it is clean. With this, we can calculate access to clean cooking. There are some complications to understand that, but because when you use an improved cook stove, there are different types with different efficiencies, and they also release smoke in different ways. So there is different CO2 emitted. For example, a basic improved cook stove uses between 20 to 40% less fuel than a traditional cook stove. But if you use an intermediate cook stove, you can reduce up to 60%, and an advanced improved cook stove, you can reduce by 50 to 70% fuel consumption. Same for smoke release, it can vary considerably. Therefore, it is important to know which cook stove a household is using, as the impact is different. Some people use different cook stoves for different meals cooking in the same household. So the task is even more complicated to collect all this information. At the IEA, we have tried to analyze the trade-offs between the different cooking fuels and technologies and gave them a score based on different criteria. There is the stove cost, so the traditional biomass is most advantageous because you just need to put free wood. For fuel costs, here you have to pay for electricity or LPG, and this is a disadvantage because here we have a problem of affordability. Then we take into account reliability, health impact, because if you are not using clean cooking fuels such as coal, this is a disadvantage for health. There is also the gender inequality, as it is mostly women that collect wood for cooking, and there is also the environmental impact to take into account. Now, let us look at an analysis that the World Energy Outlook team did on the status of access to clean cooking and tracking progress of what has been done lately. Globally, the average number of people without access to clean cooking has been stable since 2000. But if you look at sub-Saharan Africa, the share has been constantly increasing, and in 2018 it reached 35% of the world. This is because population has been increasing faster than tools to help people access clean cooking facilities. The IEA has been working on energy access issues on the continent for nearly 2 decades. Africa's population is among the fastest growing and youngest in the world. The situation for clean cooking is more concerning, as the number of people gaining access barely exceeds population growth. Population relying on traditional use of biomass, kerosene, or coal increases from around 900 million people in 2018 to nearly 1 billion people in 2030. This has grave health, social, and environmental consequences, and the resulting household air pollution from traditional uses of biomass continues to cause 500,000 premature deaths a year. Now, why do we need to make projections for cooking? Making projections on access to clean cooking and on cooking fuels enable us first to estimate the number of people with clean cooking and track the SDG 7.1 indicators. It also helps us to better understand the future energy demand based on the portfolio of cooking technologies. It also helps us anticipate the supply of cooking fuels and its related investment. And finally, it helps us to assess the impact related to cooking, the health, climate, and environmental impacts. This is an example of fuel wood consumption and its impact on forests based on two IEA scenarios. The stated policy scenario is the scenario that is based on countries' announced policies, and the Africa case, it's a new scenario that achieves the continent's inclusive and sustainable vision for accelerated economic and industrial development, accompanied by the achievement of full access to electricity and clean cooking. Fuel wood consumption up to 2040 in the stated policy scenario keeps increasing in all these countries, and the forest keeps depleting. If we don't do anything, the impact on the environment will be terrible. However, in the Africa case, consumption of fuel would decrease, and so does the impact on forests because of less wood being cut. This is linked to an accelerated move away from the use of solid biomass and to the wide application of energy efficiency policies. The shift in the energy mix away from biomass towards modern energy sources such as renewable and natural gas results in major efficiency gains and accelerated uptake of other fuels for cooking. For example, cooking with LPG uses around 5 times less energy for one meal than cooking the same meal with traditional use of biomass in inefficient stoves. Now, let us see some of the key principles for modeling clean cooking access and the general principles for modeling as seen in the modeling sessions before. We need first to analyze the drivers such as population and cooking practices. With the drivers and some econometric analysis, we get the energy services demand, which is the useful energy demand needed to cook a meal. To cook, you need a portfolio of cooking fuels and equipment. You have to do a technology fuel reallocation. You can do a cost-based approach as well. So how many households will be cooking with LPG, will be cooking with traditional use of biomass, etc. in the future? Based on the efficiencies of these technologies and the useful energy demand, you can then calculate your final energy demand. And you can also calculate the amount of energy needed to produce in the country. The challenge here is how to allocate the technologies to population. First, Not all households have access to clean cooking technologies. Therefore, we need to look at service demand separately for those who do and do not have access. For those who have access, there is a wider choice of technology and fuel based on fuel availability, cost, cultural preferences, etc. For those who do not have access, the choice is restricted and limited to the cheapest and free options, and whatever fuel is available locally. Other options not available or not affordable, therefore they choose the traditional use of biomass, kerosene, or coal. We also need to look at how the number of people with and without access may change and what can drive this change. So, with policies and market evolutions based on characteristics of each fuel equipment, and also how and when will they gain access and shift to cleaner fuels and equipments. With all this information, we can derive the number of people gaining access. Let us look at some of the results that the IEA got based on analysis done. Our analysis showed that in sub-Saharan Africa, the number of people without access to clean cooking will not decline drastically by 2030 in the stated policy scenario, which is the objective of the Sustainable Development Goals. So this scenario does not provide the right tool to achieve full access by 2030 and fix the affordability issue and the change in cooking habits. However, in the sustainable development scenario where we achieve full access by 2030, we see that sub-Saharan Africa, which in 2010 had less than 20% access to clean cooking, will reach full access by 2030. But how is this done? In 2018, 87% of the population in sub-Saharan Africa still lack access to clean cooking, and the fuel mix still has a lot of not clean fuels. In the stated policy scenario, more people gain access to clean fuels and technologies for cooking by 2030, but 70% of the population still lack access. To bridge the gap and achieve full access to clean cooking for all in the Africa case, LPG is the most scalable solution for urban settlements, with improved biomass cook stoves doing most to provide access in rural areas. LPG is the best solution as more than half of urban households gain access by 2030 as the population density justifies investment in the necessary infrastructure. In rural areas home to the majority of those without access, improved cook stoves are by far the preferred solution, dramatically improving the efficiency of bioenergy use. Electrification, biogas, ethanol, and other solutions also play important roles with their uptake depending on local context. Policies will continue to remain essential to push these solutions. In Côte d'Ivoire, for example, the national plan seeks to promote LPG use and increase efficiency of charcoal production. Therefore, despite progress in several countries, current and planned efforts to provide access to clean cooking barely outpace population growth.
Okay, perfect. I hope everything was clear. You enjoyed this presentation by my colleague Zakia that you already know because of the first part of this webinar program dedicated to statistics. So before moving to the electricity access, so the access to electricity component of the SDG7, I would like to have a quick exercise with you, which is focused on this first part on clean cooking. You already have, as usual, this exercise. I don't know if some of you already tried to do it. Otherwise, I invite you to do so maybe after today's webinar. You have the text in the PDF handbook, and you also have the Excel file in which you can find the sheet which refers to this exercise, and you can go first having a look to the clean, let's say, version of the exercise, and then move to the solutions. So I will go directly to the solutions, since we have, it's just as usual to have just a look at what is the methodology, what is the approach, etc. And then, as I said, I invite you to try to do it by yourself, not looking at the solutions. And then if you have doubts, to go through the solutions, and then if you still have doubts and something is not clear, or maybe something isn't yeah, as you expected it to be, feel free to write me. You have my email at the beginning of all the presentations. So this exercise is, as usual, very simplified modeling exercise, but which can give you, let's say, a grasp of what we are used to do at the IEA. And then, in general, starting from these, you can complicate the exercise, taking into account different assumptions. So we will go through it and see a bit what are the assumptions in this case, what are the questions, what are the yeah, the answer you can give, for example, a decision maker. So under this, let's say, short, as I said, short simplified exercise, you were put in a situation, in a specific situation. So you were asked by the Ministry of Energy of this, as usual, hypothetical country, to foresee or forecast what could happen in this country for clean cooking. So for the clean cooking usage in terms of consumption of fuel for cooking. So what you were given at the beginning was based on, for example, a national household survey, which estimated the number of people which are relying currently, like which have been relying from, for example, 2015, which have been relying on specific fuels. So as you can see, you have 4 different fuels. You have traditional wood stoves, then you have people using improved cookstoves, then you have people using LPG, and you have people cooking using electricity. So you can already see how the vast majority is using traditional wood stove, and then we have improved stoves, LPGs, and electricity, which are more or less the same, even though we have different trends, different changes. We have improved cookstoves, which, for example, had a doubling in 5 years. On the other hand, LPG and electricity increased, but not at the same rate, but are still, let's say, still have higher share with respect to the improved cookstove. So the first question you were asked, which is here, is to calculate the share of population having access to clean cooking under the definition we discussed today. You have heard it from my colleague Zakia. So we start by defining what is clean cooking, and that also comes from the SDG7 from the United Nations. And you're asked to calculate in this historical, because I remind you, these are historical data because we are looking at the past. You are asked to calculate which is the percentage of people having access to clean cooking. So if you remember, we define clean cooking as being having one of these 3 technology solutions for cooking. So what you have to do is just the summation of these 3 values, and you can divide the sum of these 3 values by the total population, which also comes from the survey, and you will have the trend in terms of clean cooking access. So you can see how in 5 years this percentage increased by 10%. Second, okay. Second, question 1 actually, which is the second question. You were asked to estimate what is the useful energy required for cooking at the level of an household. and you have some specific, you are given some assumptions that of course could be improved, could be challenged. They really depend on the context. But in this case, these are the assumptions you were given. So the first assumption is that you assume that taking like to cook an average meal in an average household in this hypothetical country, we need 1 kilowatt hour. So 1 kilowatt hour is required, and you can find it here. Then the next assumption is that people have on average 2.2 meals per day over 300 days cooking at home, where 300 days cooking at home means, for example, that some days might be cooked elsewhere, in case, for example, of public holidays, for example, or other specific days. So we assume that over the 365 or 66 days in a year, 300 on average are cooked inside, like at the household level. And then you have another assumption, which is the number of people living in an average household. So the average household occupancy, which for this country is exactly 4. Okay, so based on this number, it was possible to calculate by multiplying those different parameters what is the annual cooking energy per household. So, for example, you can calculate the annual cooking energy per household just by multiplying number of meals by the energy you need for cooking energy. Each meal, and you multiply this by the days cooking per day. But the question was asking you both at the household and the per capita level. So what you have to do is to divide this value by 4, which is the household occupancy, and you will have the annual cooking energy per capita. And you can see how these values, in this case, you don't have conversions to take care of because everything was in kilowatt hour. So second question number 2 is based on this number and on the data we got, for example, from the surveys that come from as an input. And I skipped this part because it wasn't necessary, but you also have input data related to the efficiency of all these technologies. So you can see first that all the efficiencies are constant. So we are not assuming like an improvement in the efficiency of these 4 technologies, but you can see the very different efficiency of all these 4. We have 15% for traditional stoves. We have 30% for improved stoves. We have 50% for LPG stoves, and we have 80% for the electricity stoves. So as I was saying, you can use also this value, because what you are asked in question number 2 is to estimate the energy demand for cooking in terawatt hours at the national level for each of those countries. Each of these technologies. So you can see first that the unit of measurement now is terawatt hours. So you will have to take into account to change the unit of measurement and to pay attention to that. What we can do is for electricity, for example. So let's take electricity. We could look at the number of people relying on electricity, which comes from this line number 9. We have 5 million people. Then we could, for example, multiply this value by the efficiency of an electric cook stove, which comes here, and by the annual cooking energy per capita. So you will have the estimated energy demand for cooking, for example, for electricity. You can do the same for the other technologies, and you can also do it for the projections with the same value, so the same approach. But later I will show you better how we deal with the projection. So reported. So sorry. So at the end, you have question 3, which is actually the 4th question, which asks you to compare the reported cooking energy demand with the estimated figure. So you add these values, so the yellow values, which come from our estimation in terms of estimated energy demand for cooking. But then you have also this box, which comes as an input, and it's the reported energy demand for cooking, which comes from the Ministry of Energy Statistics, for example, an annual report, annual statistics, etc. So, okay. So what you're asked is a simple ratio between these two values in order, and like -1, so you have to find the difference. So it's estimated energy minus, sorry, divided by the reported energy demand -1. And you can see how, for example, for electricity, we have more or less, but also for LPG, we have more or less the same values. We have, for example, the reported, so the estimated energy to be, for example, less, 5% less in terms of energy with respect to the reported one, etc. But we can see a very huge gap, because this is not the case for fuel wood. For example, we had like 50% difference between our data set and our calculation and the reported demand by the Energy Ministry. And this can be explained, for example, by the fact that, as we discussed also during the previous presentation, it's not easy to capture well the level of wood fuel consumption, and also to understand the level of efficiency of each cooking device relying on wood. And this is, for example, in this case, why we have important differences between our two data sets, because you can see 53%, 55, 57, till 60.2%. Sorry, 52% of differences with respect to the reported energy demand. So last question, number 4, was looking at modeling and making projections. So what could the future look like in terms of people relying on fuels? So in terms of people having access to clean cooking, so we have to come back to the top part of our Excel file. We were given already some projections, as I spoiled you. Okay. We were given some projection under stated policy scenario, which I remind you is the scenario which has all assumptions which are in line with the policies stated by all governments and ministry, in this case from Sub-Saharan Africa. So here we had 71% of people relying on, having access through clean cooking technologies. This is in terms of percentage of population, but it was also asked to do other projections, which are referred to what we call full access scenario, which, as you may imagine from the name, assume like is a scenario in which all of the population has access to clean cooking technologies. So you can see here the value is 100% of the clean cooking access rate, but we have the people relying on cooking with traditional wood stoves, which is equal to 0 in this case. So in order to define how let's say the total population is distributed through these 3 technologies, we have to take into consideration the assumptions that are given by the text. So you will see by looking at the PDF and also the Excel file, but you will see that there are some assumptions. So you were given, for example, information that the government was deploying or as a goal having a clean is having a clean cooking policy, which is aiming at reaching 5 million people, 5 million households equipped with improved cook stove. So this value comes from the text, and you can see here how this means that, for example, we have 5 multiplied by the average household occupancy, and we can find that our goal in this full access scenario is that to have 5 million multiplied by 4 people per household. So we can see we have 20 million people relying on improved cook stove. Then, for example, for LPG, we were given some limitations in terms of capacity or threshold that the country would be able to supply at the residential level demand with LPG, because, for example, we have limited levels which are based on basically refinery capacities. So based on projects, so with this assumption, we can find that 12 million people will be relying on LPG. Then we have so at the end, what we end up is basically that the electricity, so the people relying on electricity, is the total population minus the sum of people clearly relying on LPG and on electricity. So at the end, you will see by looking clearly, you can do a lot of charts. Here you have some examples. You will see how what's the difference, for example, between 2020 and 2030 when talking about stated policies. You can see clearly the trend in clean cooking access. You can plot it to see how, for example, this will change till 2030. In this case, we are not investigating on a year-by-year basis this interval between 2020 and 2030. That's why you have this gap. But clearly, you can change. You can try to do a regression to see how how the trend here would look like to reach this value on a yearly basis. You can see the cooking and use demand divided by type of technology during the years. So you can do many charts, many calculations. Okay, so I will go back to the next topic, which, as I anticipated you, is related to the other aspect of the SDG 7.1, which is access to electricity. So let me know if everything.
We will now discuss access to electricity, starting by giving an overview. We will now discuss access to electricity, starting by giving an overview of electricity access, then discussing data, and last. So the world has been electrifying very fast, and you can see on this figure, starting at the year 1990, that in all regions, electricity output has increased even more in non-OECD countries and regions like Sub-Saharan Africa. This comes from higher population and GDP with higher access, but also from higher demand at the per capita level, with each household having more appliances and more needs for electricity. Still, according to our latest analysis in the year 2019, still 770 million people don't have access to electricity and rely on stopgap and very basic technologies for basic needs such as lighting. So why does electricity access matter? Electricity access is under the Sustainable Development Goal number 7, of ensuring access to affordable, reliable, sustainable, and modern energy for all. And more specifically, it's under 7.1.1 indicator, but energy access is really at the heart of the SDGs. We often say that it is the golden thread weaving together human development, economic growth, and sustainability, because providing energy is at the base of enabling other SDGs. And we'll see a few examples. Energy and electricity access is very much related to SDG number one of ending poverty, for example, by providing sustainable lighting products such as solar lamps instead of expensive stopgap solutions like kerosene lamps that poor households may be using. Plus, there are many relations between energy and economic development related to SDG number 8 and also to opportunities for women and SDG number 5. There are also interlinkages with climate, and providing clean energy sources would displace polluting fuels such as diesel used in generators or oil products such as kerosene used for lighting. SDG 7 and energy is also very much related to SDG number 6 and 2 under the water, food, energy nexus, since we can improve agricultural productivity and water management thanks to energy. Then energy is very much related to SDG number 3 with health services benefiting from power and also with improved indoor air when there are some clean sources of lighting, for example. And last, with energy, we can get better conditions for studying at home with better lighting services, for instance, and also better schools services when schools are electrified. Let's detail a bit the relation between energy and incomes and the economy. On this figure, you can see how the share of population having access is expressed as a function of GDP per capita. And there is a strong correlation under this logarithmic curve, which means that higher levels of wealth drive higher level of consumption per capita and access to electricity, but vice versa, when we increase access to electricity, this has a potential to boost wealth. When looking at health and education, based on a study conducted in 2018, 60% of health institutions were without reliable power in certain number of geographies. And you can see discrepancies across countries. You can see countries where health centers are primarily relying on grid or sometimes on off grid solutions, and also places where there is no electricity and reliable source to power those health institutions. Coming to education, we have between 50 and 60% of schools which are unelectrified, again with strong discrepancies and with some variability in the source of power. This can come from the grid or from off-grid sources. Now let's have a look at the status of electricity access and the number of people deprived of electricity per region. So we'll start looking at the evolution over the past 2 decades. This blue space is the number of people in Africa without access to electricity, and you will see that it has increased until the year 2010 and then remained stable at around 600 million people. And when we look at other parts of the world, it is striking to see that at the beginning of the century, India and rest of Asia were concentrating almost as many people without electricity as Africa, but those numbers have sharply declined, and now electricity access is increasingly a challenge for sub-Saharan Africa. You can look at the breakdown per region in in Africa, with of course some regions where we have important countries. We can think of DRC, which is a very heavy weight for Central Africa, or of Nigeria, which is also important for West Africa, concentrating close to 70 million people without access to electricity. So in terms of region, India was the #1 region concentrating people without access in the year 2000, but this has decreased as India reached universal access in the past years. On the contrary, regions such as West Africa and Eastern Africa have come to the top ranks of the ranking. If we look again in the past at what happened in India, but also in China, you would see here how long it took to those two countries to provide electricity to 600 million people. So in the case of China, this took 35 years. And for India, it took a bit more than 15 years. And this is the fastest electrification experience we have observed in humanity, with a very impressive and strong progress achieved in India. So when we see this kind of acceleration, we can expect that in Africa, it is also possible to provide access to electricity to 600 million people before the end of the decade, so in a shorter period of time, because of all the lessons learned and the technological improvements that we now have at our disposal. And there is also some very good progress observed in many countries all across the continent. Just to shed light on East Africa, we have seen in Kenya an increase by 50 percentage points in the electricity access rate between 2013 and 2018, so amounting for around 25 million people getting access. We have seen the same number of people in Ethiopia getting access to electricity, and also in Rwanda, a very strong increase in the electrification rate. So we can have a look at electrification rate in the world, and this is the other side of those numbers on number of people with or without electricity. You would see here that sub-Saharan Africa rate for population with access is today at around 45%. So reflecting the 600 million people without electricity access. Looking with a zoom in the different sub-Saharan African regions, you can see again the strong increase in East African electricity access rate over the past few years. And you would also see the difference between different regions, West Africa being at the highest level in terms of electrification rate, whereas Central Africa has the lowest electrification rate of the continent. And on this map, you can see country by country the number of people deprived of electricity and the rate of population with the different blue colors you can see. So another way of looking at electricity access is by the fuel or the technology and the solutions which are providing access. And this is an analysis we've been doing, looking at the annual number of people gaining access to electricity by type of fuel and by technology between the year 2000 and 2012, and then between 2012 and 2015. And what you can see here is first an acceleration. On average, there were more people gaining access to electricity in the second period observed than under the first one. Then you can also see that looking at the different fuels and technologies providing access, there is a stronger role for decentralized solutions and solar PV when we look at the more recent period. But you can also see that there are some important provision of electricity to people gaining access based on coal. And this is more striking if we deep dive more into what happened in India. So this is the number of people gaining access to electricity in India over the period 2000-2016. And you would see that on average, 30 million people were gaining access to electricity every year, and 80% of them were gaining it thanks to grid extension, grid being powered by coal-fired power plant. So this is also some interesting analysis we can do, looking behind the number of people gaining access. What is the technology to provide it, and what is the fuel, the source of energy to generate those electrons? Let's have a look at the latest numbers we have at the IEA by collecting year after year and looking at every country, the numbers of people with and without electricity. So looking more specifically at Africa, this is what we observed. So a rise in the number of people without access to electricity until the year 2013. And this is because every year the demographic growth was outpacing the efforts of the governments to provide more electricity, to extend and densify the grid, or to support rural electrification programs and deployment of mini grid and solar home system. But since the year 2013, this number was decreasing, meaning that progress were faster than population growth until the year 2019, because due to the pandemic and its aftermath, we have observed that the progress are being reversed, and that in the year 2020, there are more people without electricity than there was in the year 2019. So this is a very concerning trend that needs to be reversed if we want to reach the goal of universal access to electricity by the end of the decade. And on the right part of the chart of the slide, you would see how those number of people without access are broken down by country, and 5 countries, so DRC, Nigeria, Ethiopia, Tanzania, and Uganda, are actually concentrating half of those African people without electricity. There are many reasons that can explain this rise in the number of people without access in the year 2020 due to the pandemic and its aftermath. Governments had to shift priorities to the more urgent task, so limiting support to some electrification program, or limiting some policy priority given to expanding electricity access. But if we look at private sector-led initiatives like mini grids and solar home system distribution, we have also seen some disruption in the year 2020 in the value chains. For example, it was more difficult to import products due to the international constraints. It was more difficult to distribute products to the last mile and in rural areas due to lockdown and containment in the countries, etc. So we have seen such difficulties preventing the progress that were observed in providing more electricity services, may it be through grid extension, densification, or through mini grid projects or solar home system distribution. An additional point is that, according to our analysis, there are people who were connected to the grid or were able to benefit from electricity access, but due to the economic consequences of the pandemic, might lose the ability to afford those services. So we estimate that in Africa, 30 million people could lose access to electricity, and by the end of the decade, under current policies and trends, we would expect that 630 million people would still be in the dark. Okay, now let's enter more into the definition of electricity access. So it's important to have in mind that there is no single internationally adopted definition and different ways of approaching this topic. When we discuss access to electricity, we shall bear in mind that there are different technological solutions and also several uses of electricity. So on this simplified chart, you would see different technologies, and on the lines, you would see the type of service that households and community would expect, and also more productive uses. We have basically classified it with pico solar products, such as a solar lantern that would have its independent solar panel, battery integrated into lighting systems, which might also include radio. So this type of service of product is able to provide household and community with lighting, entertainment services, especially if those devices are very energy efficient. And we are observing very fast progress in the development of such technologies with strong improvements in performances and decrease in costs. Then we have solar home systems that would include high efficient appliances like TV, fans, and would rely on as well independent solar panel plus standalone batteries and lighting bulbs, radio, torch, and other appliances. And this again can be of the use of households, but also of communities, and potentially also of some productive use if it may include solar pumps, for example. Then we enter into a higher level of energy development and service with mini grids, which are small infrastructure developed at the size of a community or a village or specific needs, and who would rely on different energy sources. It can be small hydro, it can be wind, it can be solar PV, coupled with storage or coupled with backup generator, and that will be able to transmit and distribute electricity to a large set of customers. And last comes what is the most well-known and common way of providing electricity, which is the usual grid. And as you would see, the higher you go in the type of technology solution, the more services you can provide. At the IEA, we define electricity access under the below definition. Electricity access entails a household having initial access to sufficient electricity to power a basic bundle of energy services. So this, as a minimum, would be lighting devices, plus phone charging, plus a radio, plus potentially a fan or a TV, but also with a level of service capable of growing over time. So to be more concretely, what do we consider as being access to electricity and what is not, is what you can see with this red rectangle, with IEA starting with solar home system and not taking into consideration the smallest solar lanterns. As we just mentioned, there are different options and technologies to provide electricity access, and the main one is the grid. Still, there are some challenges coming with grid-based power systems. And just to mention one, as you would know, there are some losses which are due to the nature of how networks work. But in the case of Africa, we observe some very high level of losses, which is around 6% above the average in developing countries, with in some countries like Ethiopia or Mali, some levels of losses which can be as high as 25%. So these have, of course, consequences for the utility economics, for the power generation, and for the level of service which is provided to end customers. Another way of looking at one challenge for grids and utilities is the outages that can be observed in countries like Nigeria. Our analyses have shown that it can be up to 40% of annual outages over the year, and this can lead customers to rely on backup generators, which will be able to supply some electricity when there is an outage or a blackout of the central grid. And again, in the case of Nigeria, we have estimated that close to 20 terawatt hour of electricity was generated thanks to those backup diesel generators. Then there are other challenges for providing electricity access to all using the grid. For example, some population are under the grid, so close to grid transmission lines, but not connected. And then we have in the least populated areas and the least dense rural settlements, difficulties to extend the grid to those places. When we look at mini grids, there are also some key challenges. One of them relates to finance and economics because capex or investment cost can be relatively high, as well as opex, and especially the operation and maintenance cost. And on the contrary, revenues might be uncertain, with risk of low consumptions, low ability to pay from households, for example, or for the need for an anchor client like a telecom power or an hospital or a strong commercial or industrial customer to be the main customer to ensure that it's economically possible to also provide electricity to smaller customers such as households. Another challenge relates to scalability because each mini-grid project requires some local adjustments. It needs to be adapted to the local potential for generating electricity, be it from solar PV, from a small hydro resource, or from wind. So this needs to be customized, and in front of that, demand needs also to be well estimated based on population, future estimated demand for this specific community or settlement. So it's not easy to develop in the same time or very quickly a very large number of mini grids, even though scale is possible. And then administrative process can also be long because a mini grid is a small infrastructure, so it requires, of course, some administrative work to get, for example, license. It depends on each country context, but the deployment time can be long. And last, there are always some questions on the integration with the grid once the grid arrives. There are many ways of solving these issues, but again, it will be depend on the national context. Last, standalone systems such as solar home systems also bring some key challenges and difficulties. First, this is more about distribution than about infrastructure to ensure that people can have at home a solar home system providing lighting plus TV plus fan services is a question of distribution. So the business model is more looking like what fast moving consumer goods or equipment sellers develop rather than a business like utilities or big energy infrastructure players are used to. So it's a very different mindset. Then it's increasingly relying on digital technologies because such products that might have a high upfront cost are usually sold under pay-as-you-go business models, where the customer would be able to pay day after day small installments before becoming fully owner of his TV solar home system after 1 year and 2 years. But this requires mobile banking services as well as strong connectivity. Then all those products have a limited lifetime. So thinking from the beginning at recycling is key. And last, usually those solar home system distribution models have been led by private sector players who are really relying on market-based approach. So they sell to a bankable customer, and this type of approach is not adequate for everyone. So, for example, if it comes to provide electricity services to very isolated or very fragile communities, like in refugee camps, such private approach are not adapted. So we estimate at the IEA that to reach universal access to electricity, we need to rely on all those solutions, grid extension as well as grid densification, but also mini grid and standalone system. And to back this statement, we have conducted geospatial analysis looking at every squared kilometer in sub-Saharan Africa, looking at where the population is, where the infrastructure are, where the existing transmission lines are, and depending on the cost of each technology, we have come with analysis on where it makes most sense and where it's more economical to develop further grid versus where it's more economical to develop mini grids or to distribute solar home system. And you can see that this type of analysis was done at the scale of the continent, but also for specific countries. And here you have the example of Cote d'Ivoire in Western Africa. Another example which confirms that full access requires integrated plans combining on and off grid is the very interesting case of Togo. So this Western African country that you can see here is not very is around 50 kilometers from west to east, but around 800 kilometers from north to south. And there is already a high-level transmission line which goes from north to south. So when you think of providing more electricity services to all, you might think that it's easy and it's economical to rely on the grid and just to extend new lines from this existing vertical strong line, which is already here and which is not very far from any community in the country. But what the analysis conducted by the government show is that it's not economical and it's better to also rely on mini grids and on solar home systems. So this is the integrated strategy named CISO in Togo, which relies on extending and densifying the grid in some areas, but also partnering with private sector under license schemes to develop mini grids and solar home system. We will now discuss data collection, reporting, and indicators for access to electricity. So first, there are many barriers and limitations to tracking access to electricity and off-grid. Some of them relate to survey and sampling techniques. Other relate to the off-grid source of electricity, like mini grids or solar home system, which, for example, are not metered or would present difficulties in giving some data in terms of capacity or electricity generation. Then calculating the rate of electricity access itself would involve many parameters, looking at binary information or gradual and tiered level of access, looking at the source of access, looking at per capita power consumption, or tracking also the lifetime of equipments to ensure that access is maintained over time. There are mainly two sources for tracking electricity access, and this is what is currently done today. The first source are surveys, and this is reflecting a demand size vision of access with DHS or local demographics surveys asking to households their source of lighting and getting an understanding whether households have or have not access to electricity and which source is providing electricity, grid, mini grid, solar home system. This is a survey, so it's not updated every year, and samples need to be carefully selected. But it gives a very good field and bottom up view of electricity access. And this is what the World Bank is using, for example, in its database. The second source, and which is what the IEA has been using, are government reported supply side data, mostly coming from the utility, and that can be updated every year based on the number of connections, based on the number of lines and meters that utilities would know. And it can also take into consideration off-grid data such as rural electrification government-led programs or even data coming from the private sector. This is more reflecting a supply side vision of access. Then there are new types of data, new methodologies which are currently developed, and the IEA is also very much working on improving the understanding of electricity access. So we are looking for more data on the type of connection, the availability of electricity, reliability, also information related to finance and affordability from the household perspective, quality of the electricity, cleanness, or in other words, what is the source of power generation behind the technical option. And this can come through better surveys with more specific and detailed questions or more granular data from programs and energy providers. Then, beyond households, there is also interesting work being done to understand better how health centers, public buildings, or schools are connected to electricity. One example developed by the World Bank is a multi-tier framework, so it's still relying on surveys and it enables to understand different tiers or level of service of access to electricity rather than a binary information of a household has or has not access to electricity. There are also increasingly off-grid data which are developed and which are feeding some consolidation and data tracking systems. Here is an example in Zambia under the Edison platform related to a grant program where there is a live tracking of solar home system and mini grid connections relying on smart meters and other tracking technologies developed by those solutions. Then there are also increasingly geospatial and satellite data that can help track better access to electricity using nightlight images, day PV panel recognition, or also electricity networks maps. Now we will discuss modeling of access to electricity, or how can we make projections on how electricity access will evolve in the future. So, as always, when we do some modeling exercise, we need to start by wondering what question do we want to answer. And here, again, we can take a scenario approach with deductive scenario. What will the future will look like under certain hypotheses? For example, if the current announced policies are effectively implemented, if the known technologies are developing as we expect, or we can take a normative approach. What is the pathway if we want a specific future to meet given targets? For example, what's the trajectory between now and 2030 if we want universal access to electricity by the end of the decade? So when it comes to access to electricity, some questions we want to answer are: how many people have access today and will gain access every year in the future? How much electricity demand will come from those newly connected households, and how will that feed the overall demand for electricity? Then, once we know demand, we can look at supply and see how this demand will be supplied, how we will match this level of electricity demand, and by which portfolio of solutions. Again, it can be on-grid or off-grid, and by which type of fuels. We can have questions related to investment. How much investment will be needed to serve the demand? And we can also investigate impacts and see, for example, what are the energy access related CO2 emissions. Here we will present very synthetically how we do this kind of modeling exercise at the IEA under the World Energy Model. So we have first an electricity access database tracking all the policies, looking at electrification projections on the one hand, and on the other hand, we have information on consumptions level per capita. Based on those two, we will be able to estimate what the additional electricity demand due to access or to new population gaining access to electricity will be in the future. And we'll be able to allocate this electricity access to different sub disaggregated services behind our residential module modeling. So will that demand will be for lighting, for cooking, for powering appliances, for water heating, etc. And we will be able to allocate all this in specific energy services. Then comes the power generation module, where we look at what supply can match this demand. And to do that, we have developed, based on geospatial analysis, some modeling work to understand what is the best mix of solution: grid extension, grid densification, mini grid infrastructure, or solar home system to meet this future demand for electricity. And with that, we will get information on demand by each solution and reflected into both generation terms and capacity terms. Let's have a look at a few examples of those results of the modeling outlook. Here you can see electricity demand in 2018 in sub-Saharan Africa, and how it would evolve in the coming decades, depending on the scenario, and also looking at what is the demand coming from people already connected to electricity today and from people gaining access, and then what's the demand for non-household productive use or transport. We can also modelize efficiency savings. So what will be the demand if we take into consideration strong energy efficiency policies and more efficient appliances and equipments, or if we don't? Another example on the results of our modeling is on the power reliability. As we discussed, we know that in Africa today, many countries are experiencing a certain level of outages, of transportation and distribution losses, and as a result, a high number of backup generators used by consumers. All these elements will evolve in the future. Again, we are getting projections under our different scenario as output of our modeling exercise on electricity access. Investment is also an output of the modeling exercise. We will see for different regions what are the required annual investments in access to electricity under a stated policies or steps scenario, taking into account announced policies, or under a sustainable development scenario that was, let's say, equivalent to the Africa case, where we reach universal access. And this kind of investment can be broken down: technology, grid, and off-grid solutions. A last example is on the effects of the access results on greenhouse gases emissions. And here, this analysis can consolidate our projection on access to clean cooking and on access to electricity. So let's have a look in the stated policy scenario. What are the emissions related to cooking and to electricity under the stated policies at the end of the decade? To go from the stated policies to between today and 2030, we see that we will have a reduction in traditional use of biomass that would limit the growth of greenhouse gases emissions. Under a sustainable development scenario, we have a higher level of emissions because of more people using LPG, because of more access to electricity, which will also be generating greenhouse gases emissions. But with more people shifting away from traditional use of biomass, we have a net negative change, meaning that under a scenario where everyone has access to both electricity and clean cooking, there are less there are less CO2 and methane emissions than under today's situation. So universal access will not be at the expense of climate and of emissions.
Okay, perfect. I hope you enjoyed also this part of today's lecture, today's webinar. So now, before closing, I would like to dedicate a few minutes. It depends. I don't see any question in the Q&A box, and neither I see raised hand. So feel free to profit of this moment if you have specific questions or doubts, or you want to give me your perspective, for example, about Kenya, both with respect to clean cooking and access to electricity. In the meantime, I remind you that we have an additional lecture Thursday, and then we will close next Tuesday. If you have another additional information, as usual, by the end of the day, you will have on YouTube available today's recording, so that you can rewatch today's lecture, today's webinar. And if you have doubts, feel free to write me. You have my email. Any doubts you may have, I will be very more than happy to help you get through it. Moreover, you have the exercise we did quickly. You have both the handbook and the Excel files with all the solutions. So I don't see any questions, so just a few seconds. Otherwise, I would close here today's session and wish you a pleasant day and see you on Thursday.